Hello. Good morning. Okay. Okay, so this morning, we are going to be continuing talking about applying Agile to data science projects. And we have a sprint defined here, and you can see that it is almost done. The only thing that's remaining in the sprint is this find external data sources option. And I'm actually going to reschedule that. The reason why is this is something that I prefer to do in this explore section after we've already scrubbed our data completely. And that's just a personal preference as a data scientist. As you can tell here, we did discuss external forces and we came up with a bunch of ideas. But I want to push this off here. And so our checklist is complete. We need to move our card size down. And we have 0 story points remaining. Now, we did have at one point something under this statistician sprint, but I'm going to update this to data science. Now, I know that last time I renamed this. I think that I'm going to keep all of the data science sprints in this card and just change the number of total story points that we're working with, and that way we can see kind of a project breakdown for each of our different users by the end. Um, okay, so the first thing that we need to do is we need to add a new checklist, and we're going to call this checklist sprint. And this is going to be for this upcoming week and moving forward. So I'm going to call it today's date, basically. And we're not copying over any items. I'm wondering if we can move. Yeah, we can hide checked items. That way the clutter isn't there. So we can see that 100% of this sprint is done and 0% of this upcoming sprint is done. And we need to figure out kind of what we're going to be doing next. So this is kind of like I said, this is to discuss and talk about management of a data science project. I know last week, whenever we had this particular stream, that we created a bunch of cards from kind of our overall project tracker that's in this different space here. And we looked at this current project and we looked at, these particular checklists to kind of figure out what's going on. We have considered external data sources. We need to pull those in later. All of our import libraries, those, I've talked about this a little bit, but basically we want to make sure that we import all of the libraries for the project at the very beginning. So this import library section is something that we're going to wrap back around to at the very end. Then we have develop general structure for future model. We did do that last week. Then find information on potential issues in the data set. We also did that last week. So these other two to-do items, we're going to wrap back around at the end of the project. And the same goes for these items, these remaining items here in the repo. So we're actually moving on to Scrub this week. So we need to make sure that we clean up column names, we manage all of our nans, our duplicates, our infinite numbers, we figure out how we're going to modify any of these particular things. Are we going to backfill? Are we going to forward fill? Are we going to use the mean? Are we going to that type of stuff, and then drop unnecessary data. So that's going to be what our focus on the sprint is, and we might touch into getting into some stats. So let's go back to our thing here. So create treatment plan for overall structure. All trials are similar enough to be pulled into a data frame that makes sense, so that when machine learning is performed, associations are true associations. Are there 3 trials for every concentration? That's the overall structure of data. Then I think here, create treatment for presence. This is more about statistics. So I'm actually going to move this into explore here. Then we have evaluate data types, and we don't have any acceptance criteria there. Are there 3 trials for every concentration? So this is functionally complete, meaning we have done this, but we haven't printed out, yes, there are 3 trials for every concentration. This is something that I think we should probably work on this upcoming week. So I'm going to add that to our data science sprint here. And again, you can assign these to people. And then I think this will take 1 hour. So we've got that there, and it was 4 story points, but we'd already done 2. So I'm going to add 2 story points here. And here you can see that our checklist item is going down, and it's no longer the green, everything has been checked off. Then I think that this is something, I don't want to say that this should be done before or after any particular thing that's in this list, but it is a thing that needs to be done. Then we have evaluate data types. So here I want to add the acceptance criteria. So let's do when viewing data types are all, I'm gonna say only NTG, only integer, float, and categorical data types are accepted. The follow-up to that is there should be no object data types present. And I know that we have at least one object type in our current project. So this is something that we're going to have to do. There are not any story points on this. Okay, need to create a function to do this step, and then from communication, data types for time and temperature, type data should be float. Last stream that we worked on this project, we added the concentration, which should also be, it's an integer value. It shouldn't be a float. Let's do that. Concentration should be an integer value, and the reason why it's integer versus float is there's no half concentrations. It's only like 5, 10, 15, so those should be integers. And then the trials should be categorical. And honestly, the concentration, an argument could be made that those are categorical too. However, the number that's assigned to them does have a mathematical meaning. So we're going to leave it as an integer. However, the trials, are they categories? No, they're kind of just like human made up ones. Is there something functionally different between one group and another? No, but they are labels to ensure that we have, you know, this 3 trials. And that's kind of where that begins and ends. After we do this, we can probably drop the trials. And I might do that too. Trials should be categorical. However, the trial value might be dropped after ensuring that there are 3 trials present. And I know that the last time that I worked on this project, I kind of discussed that the trial value is not really important mathematically to what's happening. And I think we can probably just get rid of it now, honestly. It was really good for reading in the files because we had different, you can't have file names that are the same. So it was good for reading in files, but I think now that we're moving more on to mathematical functionality, we don't need them as much. Um, Basically, once we ensure that there are 3 trials present, I want to drop that trial data after that. And that is going to come here where drop unnecessary data. Um, the trial data by this point is no longer necessary. It was helpful to read data into the workspace, but loses its value after file names no longer matter. I thought about that a little bit, and that's kind of my gut feeling is it doesn't have any mathematical value. Evaluate data types. We added our acceptance criteria. We did not add a card size. This is a really easy data science task. It's very quick. The reason why I'm assigning 2 story points instead of something more, if you have a ton of features and they're all objects, that can take some time to figure out, is this an integer, is it not? For this particular thing, for this particular project, I don't foresee it taking that long. Okay, then execute statistics to summarize present data status. And this is a statistician card, and that's going to move over into Explore. Ensure data is ready for future model structure. When I view pre-processed data, everything looks in order for future model structure. This is something that is going to be the very last thing that we do in this scrub section. We evaluate data types, clean column names. This is again something that I foresee going very quickly in this particular section, and the reason why is because I've already done that. Whenever I was making my data frames, I made sure that my column names were clean. One thing that I might want to look at is how to include the, what's it called? Is it a mu? Yeah, it's a mu sign for micro. That's something I'm going to want to include. Because right now, typing out micrograms is a lot, where you could just put the Greek letter mu and then grams, and that's pretty universal. There are no spaces or breaks in the column name, and the names are in the formatting necessary for visualization. So this is something that I want to do here. It's not a very expensive task. So far on here, I have create treatment plan for overall data. I want to go ahead and add this evaluate data types card to my upcoming sprint. And I think that this task is going to take approximately an hour. It might take more, it might take 2, but I kind of doubt it. Then this clean column names, again, this is something, the card size is already 2. That's something I don't foresee taking a very long time. It's really easy to update your column names. I foresee that taking, I can't give that an hour. I'm gonna give that a half hour. And this evaluate data types, I'm gonna leave it an hour because we do have to do something. Then create treatment plan, what we have remaining on that task, I think will actually functionally take an hour. Manage NANs. This is something that I think should have a card size of 4 because it takes a little bit of time to set up some stuff for this, and it's because of management. If there are any NANs, you have to figure out how to manage them. This is something I also think that we can easily accomplish this week. So I'm going to add that to the sprint. This is, what is this? Oh, managing NANs. I think this is going to take an hour as well. Okay, managing duplicates. This is something that I am uncertain if it's in the current data set or not. I honestly have no idea if we have duplicate data. I don't expect that we will, but it's very possible. And again, its card size is going to be 4 because it is a simple task, but if there is duplicate data, you have to figure out how to manage it. And that could come from backfilling, forward filling, filling by mean. This is something I can see us adding to our workload this week. And again, in 1 hour, just because of management. A lot of these things, like managing NANs, managing duplicates, managing infinite numbers, those can all be done kind of in the same space. I think I want to go back and add story points at the very end. Just because counting is hard. Again, managing infinite numbers, I'm going to go with a card size of 4. And the reason why is because figuring out what treatment to do. And the thing is, too, like, all of these could have different treatment plans in the data. Even if, you know, you can have different treatment plans based on what's going on. In all honesty, it takes maybe 5 minutes to run, but the management part can take a little bit of extra time. Drop unnecessary data. This I'm going to put a card size of 4 because you have to figure out what you're going to drop and if it's necessary or not. And that might require some communication with your domain expert because you want to make sure that you don't drop anything that is genuinely necessary to the project. I think this is going to, again, take not terribly long. And then ensure data structure so that pre-processing man hours are reduced. When I view pre-processed data, everything looks in order for future model structure. We've already spent some time on this. I'm going to go ahead and spend 4 story points just because we've done work on this already. We've done a lot of thinking and models for future model structure. We discussed some of what that might look like last week, and it's going to be really important. So we've already spent some effort on this, and now we just need to make sure that our data frame is nice and neat. We have drop unnecessary data, and then here I want to do this as well. This is a little bit more time intensive. I can see this taking around 4 hours. Okay. So that's all of the scrubbing stuff. So we have 1, 2, 3, 4, 5, 6. I'm going to lump this clean column names in with that 6. Then we have 10 hours here. So we can actually do some additional work. So that's kind of exciting. This find external data sources. Oh, first let me check. Do all of these have acceptance criteria? Just because we saw the one that did not. Okay, cool. And then did we, so all of these are, okay. Then let's, find external data sources. Is that going to happen before or after creating this treatment plan? You know what? I think that is going to come after this create treatment plan. Then execute statistics to summarize present data sources. Again, I think that's going to come before this find external data sources. Now, let's see here. I'm going to go into my explore section here, and let's see. So scrubbing, we talked about all of these things. Then we want to look at explore. We want descriptive stats, we want distribution stats. Okay, so let's go here. We know that we need to have some information about descriptive stats, and we need to have some for distribution stats. So let's go ahead and find out what some of those things might be. And let's try to find some documentation. I want to instead of doing Python, let's add in our magic word of documentation. There we go. So we have math statistics just in the base Python, where we can get so it's not intended to be a competitor to NumPy or SciPy. And then we have measures of central location. This is going to be some of our descriptive stats here. Yeah, this idea of quantiles, and then measures of spread. Again, this is going to be some descriptive stats. We have our standard deviation and variance. Then we have relationships between them. We can look at covariance, correlation, or linear regression. That's getting more into our modeling. And we see here in this base Python that we can actually look at NumPy and SciPy to also get some descriptive statistics. Let's click on documentation up here. And let's go to the user guide. Okay, then we have array creation. We're going to end up doing some array stuff. Then we have some tutorials. That's not exactly what I'm looking for, so I'm going to go to the API reference. Then we have scalar. That's cool. Standard array subclasses, mass arrays. Then we have some constants. You can see nans in here. We don't want that. Universal functions. Then we have some routines, statistics. Here we go. Then we can again get some descriptive statistics here, some correlated between two different variables. Then we can do some histograms, which is going to be good. And that's all that is here for NumPy and SciPy. Again, let's go to our documentation. Let's go straight to the API reference this time. And let's look. We have clustering, k-means, hierarchical. We have a transform here. Linear algebra. Statistical function for masked arrays. Let's look at these. So we get some descriptive statistics. That's pretty cool. We can just run one function if we use the SciPy library to get descriptive statistics. Again, kurtosis, that's a test for a statistical test. We can get some quantiles, which is really good. Then we can get plotting positions. That's pretty cool. We can look at skew. We can look at mean. These are all trimmed, and then a variation. So SciPy is usually what I go to. I usually use base Python, and then I use SciPy. Then we get frequency statistics, which is cool. Then we get much more expansive correlation functions here. Then we get into our statistical tests, uh, our t-tests and our chi-squares and some k-tests and all of the tests for those. And then we have some additional transformations here too, which is really good. So SciPy is going to be one of the libraries that we use there. So descriptive statistics in general are things that talk about. So here, to just set it up in the same format that everything else has, I'm going to put run descriptive stats. For a more detailed description, I'm going to go ahead and put in our user story as a data scientist. And then I forget the exact verbiage. If I go here, user stories, I want so that. Okay. I want to run descriptive statistics so that decisions about modeling are informed and purposeful. And it's so that business, right? So that's the data science reason that you want to run your statistics before you set up your model. You want to make informed decisions. And descriptive stats can do that for you by, painting a picture of what this table of data looks like and is doing, and it can help you figure out some of your hyperparameter tuning. The actual business value is it reduces computation time, but I don't want to put, maybe I'll put that in parentheses or something. Reduces computation time and resources, because you're not having to model over and over again. Like your first model that you run kind of out the gate might already be at 85% accuracy or something like that, versus starting from nowhere and you only have 10% accuracy. And that's exactly what I don't want. We definitely want our first model to actually be useful as a model. So acceptance criteria, when viewing information about the data, about the processed data, there should be a report, or there should be kind of a section in the final report that discusses descriptive statistics. And we have kind of our general idea of what those descriptive statistics are going to be. So labels. This is something to do. This is a story. This is coming from the data scientist, and this is definitely about the data. The final report stuff, that's going to be more of a code thing, but this is mostly about the data. I want to know about the data. So run descriptive stats. Now, I feel like we need to add something else. Develop visualizations for descriptive statistics. That I feel like is more of a code type thing. So this would be kind of like our code analog. This is a story. This is to do. As a data scientist, I want to develop visuals to go with the descriptive statistic section of a report, so that, and the business, I want effective communication here. And the reason why I think this is really important is, again, not everybody is going to be familiar with the data science portions of things, with the modeling side of things. But a lot of people in business can look at a histogram. A lot of people in business can look at, a bar distribution chart. They can look at your quantiles and they understand confidence interval. The people that are making these business decisions do have some knowledge of math. And if you say one particular, like for this particular feature, that everything is kind of clustered in this one area, then they're going to expect that to see that again. And if you say that this tightly clustered thing is a really important feature for modeling later on, they're more willing to accept that it's included later on. And so this description, this visualization is a tool that gives validity to your data science work, your modeling work, because it's very hard to put a visual on, we developed this math equation. Once you run your model, you can develop some visualizations after that, but this is kind of like the before part, right? Because you want to show a before and an after. And one way to do that is to show your descriptive statistics, your distribution statistics, show it with raw data, and then show after you've modeled. And if what you've modeled isn't comparable to what you did before, then it's not necessarily a good model. And that's the general idea. So you want to show a before and an after, and your descriptive and your distribution statistics that you run on the raw data is like your before. About the state of affairs within a data set before and after might be achieved. The acceptance criteria here is going to be when viewing the statistics section of a report, there are easy to read and understand visuals, not just random words about F values, which is something that can come from descriptive statistics. So this is more of a code thing than a data thing. We're using data, but we're mostly writing code for that data. Then for distribution stats, those are going to be a little bit different. Run distribution stats. Okay. So we looked at descriptive statistics. Now let's talk about distribution statistics. Again, we have the statistics library. Then we go into SciPy again. We have statistical functions. This is going to be things from stats models. And we looked at some of this before. This is our OLS. This is, let's go to the API reference. We have our OLS, we have some recursive stuff, we have our Bayes, then estimating equations, linear models, then discrete and count models. This is more about what I was thinking about for distribution. And then statistics, we have descriptive, and again, descriptive, then statistics, tests, and models. This is the section that is going to go under that distribution statistics. I always forget which one's which. Distribution and descriptive. And then there's another section, it's like discrete. Anyway, yeah, but there's ultimately a couple of different things that need to happen. Okay, let's actually look at distribution versus discrete statistics. It's not exactly distribution versus descriptive. Let's try descriptive. Frequency, central tendency and variability, frequencies of different responses. That's from described. I like built-in quite a bit. This would be a great article to read, and maybe I'll put that here under this run and descriptive stats. And it's great because it's specific to machine learning in this case. Here's another one that's going to be specific to data science. So there's descriptive, and let's look at distribution. Yeah, this is going to be good. We want to figure out, which distribution our particular data set kind of follows. There's, normal distribution, which is set up on bell curve. Then you have skewed left or skewed right. And then you have something with really wide kurtosis. And figuring out all of these distribution stats, just figuring out where your features fit on that bell curve and how that bell curve has been shifted away from normal, can allow you to do transformations later on. So that's going to be kind of here as a data scientist. I want to figure out the data's distribution profile so that I can make informed decisions about transformations later on. Certain transformations are really good at correcting for certain types of distributions. And so that's going to be what's great here. So my acceptance criteria is when I view the data on a bell curve, I can know how to adjust or transform the data to conform to a normal distribution. And for machine learning, it's kind of important to have your stuff look like a normal distribution. You can feed in something that is not normalized, but you need to have a pretty good reason for it. And machine learning works better with normal distributions because remember, we're like doing a test train split. And whenever you do that test train split, whenever you're removing pieces of data, you don't want to remove like one big section of data and kind of mistrain on it. And so that's the business reason why we want these distribution statistics run. So we're going to have runs, again, separately from our visualization, because to me those are different tasks. This is a story. We're doing this as a data scientist, and this is more about the data, and then for the visualization, we'll put information about the code. I was going to put communicative visualizations, but I think I'm just going to put visualizations. I don't want to put a qualifier. I want to develop visualizations for distribution, statistics, so that transformations of raw or processed, I'm not going to say processed, it's pre-processed. Like doing the transformations means that you have processed data now. Can be explained when I view these visualizations. They should tell a story. And relate to the distribution statistics. And it should be pretty obvious that they relate to that particular thing. To do, meaning we need to design it in such a way that it is obvious. Okay. And then here, I'm gonna do something a little bit different. So far we haven't talked a whole lot about pipelining. And the reason why we haven't talked as much about pipelining is this obtain and scrub is very unique to the raw data that you're getting in. If you are serving multiple clients and you're asking them for the same raw data, it does not mean that you are getting the same raw data. It's going to be structured in possibly different ways. It could come in different files. I received my raw data for this project in a text file, but it could have been a CSV. And the original file type was CMBL. And so, like, this obtain and scrub portion is going to be so unique to each data set that you get from a client. However, once you have, like, kind of a client profile, once you get, you know, and if you're expecting to receive multiple of the same data set, like for instance, they run a particular test every 6 months. Once you have the profile set up for that particular data type, then at that point you can obtain and you can pipeline your obtaining and your scrubbing. But the first time that you're interacting with a new type of data set with a new client, this obtain and scrub is not pipelinable. However, once you have here ensured data is ready for future model structure, once that part has been completed, you can actually pipeline all of the explore and model portions, and that same pipeline can be applied to every client, every client, every, you know, similar type of data that you get from every client. So here in Explore, we've talked about visualizations, and we've talked about descriptive stats, and we've talked about running, you know, statistics to summarize present data status. You know what? Oh, this is statistician. Okay, so there's some stuff that we want to do first to figure out if we should drop or aggregate or something. For that. Okay. I want to, after this, I want to write a function that uh, it's not even writing a function. It's more create a pipeline for all statistics. This is something that's going to be very, very code heavy. And I think this is the first time so far in this entire project where we're talking about pipelining. So what a pipeline is basically means you can throw anything at it and it'll output the same thing. So I want to create a pipeline for all statistics. As a data scientist, I want to create a pipeline for statistics so that it is automated and reduces man hours, like active man hours, actively doing the statistics and whatnot. The acceptance criteria here is when I run statistics, I want the process to require a start input of some kind, whether, you know, that's in our web application at the very end where you hit a button and it runs all the statistics, or it's like running your cell or whatnot, but I want this to happen with a single start input. And I'm going to put that require a single start input of some kind. And output all of the statistics performed. Let's see. Let's do man hours here, and performed should be that performed. Okay, save. This is a lot of story points, this pipelining. It's a lot because you have to write functions and then here I want to create a report section for statistics. And this is, again, this is very much a code thing. And it's a story and it's data scientist. Okay. As a data scientist, I want to write a report for statistics that is automated. So basically what that means is I want a report that's automated. I do not want to have to manually write a report for every client for every time that the data comes in, right? I want the report to have a similar look and feel each time that this is run. And that includes things like, you know, including things like it's a normal distribution or it's not a normal distribution, and these are the reasons why. I want all of that stuff to be functionalized, and that way, you know, based on the inputs, we get this output, and a paragraph is generated for us that has some verbal explanation along with the associated visualization that we're creating. So that, and again, this is so that man hours are reduced and manually generating the same report. This takes work. This right here, this takes work. When I view the report, I want to see a visualization along with a text or verbal, and it's not that it's verbal, a text explanation, explanation of what's going on in the visual. And I want this to have, when I went to see a visualization for every type of statistic that is read. Now, these can actually be broken down into simpler tasks, like run descriptive stats. I can break that down into find the mean for each feature, find the median for each feature, find the range for each feature, develop the confidence interval for each feature. Those are things that I am going to do as I get closer to that point in my project. These are very much just to remind me that I have to do these things, and then I want to go get the list of what that might be and bring it to the table. So this is, again, in this statistics portion, this is an overview. Then let's look at what else we have in our explore section here. We've talked about descriptive stats, distribution stats. Now transformations, let's go back here. We don't know exactly what transformations we might use yet, but we want to evaluate transformations for each feature. And we want to talk about why we're including them or excluding them. We want to talk about the idea that we considered what was going to happen. And that's going to be kind of like here, find information on different regression types. So we have here a list of things, and then we have some project specific, like the quantile regression and the Gaussian process regression. Those are things that I specifically want to view in this project. This transformations is going to be the same thing. We're going to have a big long laundry list of all the different types of transformations we could evaluate, and we want to look at each one and say this is a good idea or this is a bad idea. We want to create inclusion and exclusion clauses for each type of transformation. And, you know, there are some transformations that you do to the entire data set, and then there are some that you do to features independently. And again, this is something that should be reported. If you make a transformation, you need to compare how that transformation affects your data compared to the pre-processed data. So you need to have some statistics that say, yes, it's statistically different, and I think it will have better performance. You can't just put a transformation. You need to have proof of what's happening. This is a pretty big thing. We want to see, you know, that discussion about why certain transformations were considered and other ones weren't. And, you know, I want to see that or I want to see reasoning behind why certain transformations were considered, and if executed, I want to see that transformed data has been compared to the pre-processed data. This is a data thing. It's a to-do. It's a story. It's for the data scientist. I know that I have some other labels here. I have done, which you can see. I do have here done. The doing label, I think, is a little bit more useful for projects that have multiple people working on them. And the ASAP, I think, is really important whenever you have a deadline coming up. Right now, I haven't got into defect or feature very much. The reason why is because I'm at the very beginning R&D steps. Right now, I'm working mostly from stories. Features are things that go into like web apps, right? And I'm not there yet. Defects happen whenever you're in the troubleshooting stage for those web apps. So that's why I'm not really using these stories. Now, I want to go in and I'm using the code and the data label. Like, as we get on, I'm going to, after basically once the statistics is done, you swap from being primarily data focused to primarily code focused. So right now, that's why I'm using mostly data labels. As far as the other roles, the other users, I want to address this particular project first from the data science point of view. It's a lens that I haven't looked at this project through before, but I also want to go back afterwards and look at it through the lens of a chemist whenever I have all of my features and I've done my the feature analysis to figure out which ones are most important. I do want to have input from my domain expert, and in this case, it's a chemist. Actually, I think I'm gonna edit this to domain expert, and in this case, it's chemist. And then I want to look at this project through the lens of an architect. That's going to happen whenever I'm building my web app. I want to make sure that everything communicates effectively together, that I have variables loaded properly, and that the variables that need endpoints have had those endpoints generated, and those endpoints do connect to the web application. I want to make sure, so this is kind of like back-end software engineer as well. To me, I'm going to use those things interchangeably because they're not interchangeable, but I'm going to use them interchangeably to kind of delineate how I'm looking at this project. Am I looking at the content of the data as a data scientist, or am I looking at the variables as a backend engineer? Am I looking at endpoint connections as an architect? Then there's also a researcher. The domain expert chemist is going to have a different, or I guess more refined view than a researcher. A researcher basically just wants to make sure that things are being tested against each other, that variables are being tested against each other. And I think that the researcher viewpoint is going to be really interesting whenever we head into modeling. And again, looking at those features and feature importances and whatnot, I want to look at that through the lens of a researcher, but also as a chemist. Yes, this is important. Yes, these are things that are related to each other. But this is kind of like an interpreted meaning as a chemist. But they are also a domain expert in this case. And the reason why I wanted these kind of separated out is because I want to communicate the idea that you can have multiple domain experts on a project. Somebody might inform you in one way, but the value add that they have for a particular section is going to be different than if you talk to someone else that's different. And I guess you could say here, statistician, That's also going to be a domain expert, right? Especially for that stats portion and writing those reports and getting those more specific descriptive versus distribution laid out appropriately. And the statistician's point of view is going to have, you know, our I forget what they're called, but hypothesis your hypothesis not, and then your H0 and your H1. Like, that's going to be your statistician that's going to inform on how to set those up. We don't really care about that as much as a data scientist. However, if you're doing your statistics, you make sure you do it right, right? So that's kind of a little bit of a discussion on why it might feel like I'm using the same labels over and over and over again. It's because first, I want to look at this project through the lens of a data scientist. And I am going to be right back. So if y'all don't mind, chair cam. I had a phone alarm going off, and if I didn't find it, then it would bother me. And I also realized I wasn't wearing my glasses. They're blue screen filter glasses, and my eyes were actually starting to hurt. Okay, so labels. I was talking about what was going on with my labels here. So basically, I want to pull in opinions from the chemist, the researcher, and the statistician. I want to kind of put on that lens as I'm going through this particular project, because I have experience in all of these things. So I want to make sure that I address those points of view at transition points in the project, I guess you could say. Then software developer is going to come at the very end, where I turn this into a web app that I can use. Then architect is going to come with that idea too, to make sure that everything is connected and everything is set up on my web page, and the API calls are doing what they need to, and the computation space is directly linked to the project space and the web application. And that's where features and defects and stuff are going to come into play a little bit more. Okay. So we've done some things here, and we talked about transformations. We want to evaluate transformations, and then we want to execute transformations. As a data scientist, I want to execute transformations so that modeling is a bit easier later on. When I view the processed data compared to the pre-processed data. They should be different. Transformations. They should be different. And bring new statistics with them. So earlier I mentioned that I wanted to pipeline my statistics. The reason for that is because I knew with transformations I'd want to run them all over again. So I want to set up that statistics pipeline before I go into transformations. And you know, whenever you add in new data, you also want to rerun those statistics again. I'm not exactly sure where I have. Okay, I have find external before running any descriptive stats, but you might not have them at that point in time. You might end up adding those external data sources a little bit later on, and again, you want to be able to run your statistics pretty much on demand. So let's go back to our Explorer here. Labels and features, and then we do our splits. So basically here, labels and features, we want to ensure that labeled data is labeled and that features are I want to say split data into labels and features. And I'm not going to put label. I'm going to put into target and features because you might not have label data, and whenever you're doing unsupervised, you still need a target. So we want our target data and our features split up. And this is definitely a data science. This is definitely a story. This is definitely to do. I'm struggling on if this is a code thing or a data thing. I think this is a code thing. We're starting to move into machine learning here at the very end of our Explore. As a data scientist, I want to separate target and features. Target variables and feature variables. Variable. So that, and this is the really important thing about splitting your target and your feature. You do not, you don't want to include your target variable with your features in machine learning, because otherwise, I forget the specific word for it, but it's kind of like crossing the streams. You don't want to add or introduce overfitting or bias or anything like that into your model. And if you're including your target variables with your feature variables, then you're doing that exact thing. You don't want to include your y on the x's side if you're talking like mathematically with an equation. You don't want, and that's kind of what you're doing. That's how I've always pictured this splitting into targets and features is, you know, you have your y equals mx plus b, right? Whenever you're splitting them, that's the equal sign, and you want all of your target variables on one side and all of your features on the other side. You're creating your two sides of the equation here, and that's really important in machine learning because that's what we're doing with machine learning is, you know, developing an equation that has multiple variables and multiple coefficients and whatnot. You're just calculating for the coefficient. So if you don't split your equation, they're not equivalent. You can't set them equal. You can't do a whole bunch of math with it. So I want to separate target variables and feature variables so that my future model equation has the, I guess, appropriate relationships between all variables. And the business value here, to prevent overfitting and retraining, which reduces time. So my acceptance criteria here is the two variables, target and features should be completely different with no overlap and have data within them. So I'm gonna go ahead and hit save on that. And then here we are gonna do our perform a test, to train, test, validation, split. There's a lot of different ways to do these splits, but the important thing is that we do it at all. As a data scientist, I want to perform a train, test, validation split so that I can test model accuracy and validate the final model's efficacy. Okay. The acceptance criteria here is the three variables, or the three, I'm gonna call them sets. They're not really sets, but I'm gonna call them that. 3 sets of data should contain different points and rows of data. And that's going to be interesting because right now my index value for my data is time, and I actually might want to set that to my index before I do any of this stuff, so that, well, I don't know, but time is not really a variable in this case. It's more of an index. It's what's keeping the data row by row by row. So basically what's going to end up happening is we're removing times, and that's going to prevent overfitting. The idea of removing specific rows of time from our data set is going to prevent overfitting, but also it's a really good way to test accuracy later on, because you can predict those values and compare them to the actual, like you can fill in the gaps basically, and you can take those predicted values and compare them to your actual values and figure out accuracy. That's exactly what a train test split is. The validation split is a little bit different. Basically you take your train test split and then you take your test split and then you split that data again to create your validation pool, and you end up cross-validating using that particular data. The 3 sets, train, test, validation, should contain different rows of data so that, I guess I should say, like, in order to complete accuracy and validation testing. This is labels. This is a data scientist to do. Did I set this one up as a data? I set that up as a code. In that case, this would also be under code, but not data. And that's because I'm talking the 3 sets should contain different things. Okay. And I think that finishes out the explore as I have it here. Transformations. Something else that happens here under explore is develop new features. And this happens in this statistics kind of type, or it happens before the statistics phase. It's my favorite thing that happens in the explore section. Develop new features. And a lot of times these new features come from these external data sources. So I'm going to do find external data sources, develop new features. Then you run your stats to figure out if they're good or not. And if they're not good, you drop them. And then you can do some, what is it called? I have it pulled up here. Some feature importance type things, and you do those before you run your data. So here I'm gonna do feature. I'm gonna put determine feature importances, and I'm gonna do that here after execute transformations. And then if they're not important or don't contribute, you drop them. And then there's collinearity, but that's a part of statistics. Okay. Develop new features. Okay. As a data scientist, I want to develop new features using existing features so that and or external data so that modeling might be enhanced. Something that I did in one project, and this kind of like drove home this idea of new features for me, was I did this housing prices and King County project, and you know, our business question was, what can I do to my home to help it sell for more without a huge cost investment? And one thing that I did is one feature that I created, we had the number of bathrooms, the number of bedrooms in the house, and I did bathrooms per bedroom, because growing up I lived in a family of 4 people, my mom, my dad, and my sister, and we had to share a bathroom the whole time. Growing up, we only had one bathroom, and something that would have been great was if my parents could have their own bathroom. And so that's something that I've always thought is the number of bathrooms per bedroom in a home can be really powerful. And that was just something that I personally thought and experienced. And I added the feature bathrooms per bedroom to my data set, and my model performance improved like, I don't know, 60% accuracy or something. And I was the only person out of my cohort that was able to actually get statistical difference in my model based off of a new feature that I had inputted. And so that kind of sticks with me a little bit. is I want new features using existing features so that modeling might be enhanced. And our acceptance criteria here is that new features should be statistically different than other present features. And what that means is we need to make sure that they're not collinear. We want to make sure that they're not overlapping. We want to make sure that the standard deviation and the variance for this new feature is not the same as the original features that we used. Because if the standard deviation and the average and like all of these descriptive statistics are the same, then it's going to perform the same way in our future model. So we need to make sure that these new features are different than the old features. And the way to do that is with the descriptive statistics. So that's why I added my new features before I run all my statistics, so I can look at them side by side. And then in the report, then that's when you say this new feature that was added is different than the other features. And I suspect it is because the relationship between bedrooms and bathrooms, the number of bathrooms per bedroom will influence a home buyer's, like, this is my interpretation of that statistical difference, right? Will influence home buyers differently than just the number of bedrooms or the number of bathrooms in isolation. But that relationship is going to be something that affects somebody's buying decision. Yeah. And that is what good new features look like. They have to be statistically different than the other present features. And I'm going to just add here, meaning that the average and standard deviation is different. I'm going to put IE as an example. That's not by any means an exhaustive list, but it is a list. Labels, this is a data thing and data scientist story to do. Okay, so developing new features. Actually, this is more of a code thing. This is more of a code thing than a data thing. Because we're going to have to do maths to to old features to make new features. The way that I make sure that they're different in average or standard deviation usually is by doing some sort of transformation to that data. And I use the word transformation very loosely here. It's not an actual transformation, but it is a change from its existing state by doing something that's not addition or subtraction. If you take the log, if you multiply or divide, you are changing a relationship. You're changing the ability for the average and standard deviation to be the same. So that's what I typically stick to. But you have to do things that make sense for your project. And we kind of talked about that a little bit here. Number of molecules present, but I feel like the number of molecules present is going to be really similar to concentration because concentration is that adjusted feature, right? It is different than the number of, we had to do some division and stuff to get there, but ultimately molarity is just moles per liter. We have the volume. The volume is pretty consistent across all of these. I know because I made the solutions. They're all 1 liter. So we're dividing by 1. We're not really changing that value very much. And that's why I suspect the number of molecules is not going to be a great feature to use. I feel like it's going to be the same average and the same standard deviation because it's very similar to concentration. However, if we look at kinetic molecular theory, I know for a fact even before looking at the equation, that it does have some division and some multiplication in it. I think it even has an exponent. And so I feel like that will change the mean and the standard deviation from the original input data that I would be using for that. And then molecule speed. Speed is a per second thing. And so I think that would be a very interesting thing, because I already, again, I know that there's at least a division in there. There's at least a multiplication in there. Collision angle, that is transitioning from linear data to radial or degree type data. And I think that that would be interesting, because we're having to go through some maths to get there. We're having to add in a cosine, we're having to add in a sine, and having angular measurement, I think, would be really interesting. Hydrogen bonding, again, requires some multiplication, so I think it would be different. Periodic table data, I'm a little bit iffy on, because I don't think it'll be different than the number of molecules present, because of what is in that periodic table data. However, shielding and electronegativity, I think, would be really, really interesting, because they are affected by the number of, like, it's especially with hydrogen bonding or van der Waals forces, like, the more that you have present, the stronger those forces are. It's not necessarily multiplicative, it's not necessarily a quadratic or a linear function by any means, but it does have an effect, and so I think that would be really interesting. And then number of collisions, I think would be interesting, again, because it has to do with this kinetic molecular theory. And the more molecules that you have present, the more collisions that you have. It's not, and again, it's not a linear relationship. It's not a one-to-one increase. It's something different. And so we're adding in the idea to our model that this scaling might be a factor that impacts solvent changing to reaction. And I think that that's really interesting. So that talks about new features. And then here we want to go to feature importances as a data scientist. And this might happen after modeling. In fact, I do think that feature importance happens after modeling. So I'm going to go ahead and cancel this. I'm going to cancel this. And I'm going to move this over to model. It's not the first thing that we do in modeling, but it is something that is done at that point in time. And you can see here that we're starting to get kind of deep into this project. We're getting, I don't want to say the halfway point, but it's really nice to see some of these cards starting to get filled out. And I feel really confident that while this isn't an exhaustive list for things to explore, it's a pretty good one. It's a pretty good one. There's going to be some specifics that go into this particular section, and I know this is something that's really hard. You go read, what is in a data science project, as maybe a project manager that hasn't done a data science project before, and you see these words: obtain, scrub, explore, model, and interpret. And that's the OSEMN machine learning project style. There's a couple of different styles, but this is the one that I prefer because it gives me some discrete stuff. But you don't ever hear, like, what is in a scrub section, what is in an explore section, what are the things that must be present in this explore section, and what are the things that can be skipped. And this is kind of like my list of must be in an obtain section. You need the data from the database. You have to create a local space for that data and transformations, especially if you're in more of an R&D type space instead of a production space. You want to communicate that data structure that needs to happen between parties, but that it has to be communicated. What data is available in your files at all? Is it categorical? Is it float? What's going on there? And also, we talked about headers, and we found some really cool information that is going to go into this drop unnecessary data. because we looked at headers, um, discuss external data sources, what's possible, what's not possible. Usually at the beginning of the project, it's a little bit easier to be in communication with your domain experts. That's why I have this discuss external data sources and obtain. Also, you need to have the ability to obtain those data sources at the beginning before you move into the explore section. Discuss future model structure. I think this should happen at the very beginning of the project. Again, because you're setting things up, you need to obtain knowledge about what resources are going to need to happen down the line. If you're requiring deep learning, you need to make sure that you have the computation space beforehand. It's just the worst to run up to a project and get really excited about the modeling and then realize it's going to take 2 weeks, and the reason why is because your computer's slow, or you're having to pay for each transaction, and it's a little bit frustrating to find that out, this deep in the project versus the beginning. This find information on different regression types, that is specific to this particular project. However, you can find information on specific model types for the project that you're working on. Then find information on deep learning model architecture for the particular project. You need to find out if deep learning is going to be viable for your project or not. And I think the time to do that's at the very beginning. That way when people are asking you, how do you know that your model works? At the very end, whenever you're presenting, you can say, I compared a variety of model structures. These are what I compared, and this is the results of that, basically. And you want to talk about that in the beginning, because again, you want to figure out your resources that are available for the different modeling that you're doing. How many models can you run on the particular data set? Are you restricted in any way? And the time to find that out is at the beginning. Then scrubbing is very specific to particular data, but that's more of the minutia. You need to treatment plan for overall structure. That happens if you have some anomaly, like we have 4 trials instead of 3. You need to figure out what you're going to do. Evaluate data types. That should happen every single time. Cleaning up column names every time. And I do this at the beginning because it's easier at the beginning instead of changing column names at the very end. You have to manage nans every time. You have to manage duplicates every time. You have to manage your infinite numbers. You have to drop unnecessary data. These are things, and then ensure that your data is ready for future modeling. These are things that you have to do every time whenever you scrub. The contents of what that looks like are going to be different each time, and that's kind of up to the data scientist to figure out, but this is what I want to see as a manager every single time. I also want to see all of these every single time whenever I'm exploring. The minutia, find external data sources, I'm going to leave that up to the data scientist, but I want to see that they tried, new features, I want to know that they're there, and I want to know specifically if they're statistically different from the old features. And so that's kind of where this comes from, is I'm very much a bottom-up processor, and what that means is I am very good at details, but it's a little bit more difficult for me to see the bigger picture. And whenever I'm working in a data science project, I want to make sure that I'm hitting all of these points. It's a lot to track. And that's kind of where this is coming from. Now, I know that we had not quite filled out our sprint here. We have 2, 3, 4, 5, 6, 10 hours total. I want to get close to 20. So here we have ensure data is ready for future model structure. That's still in our scrub here. We set up treatment plan for present data. Create treatment plan. This is kind of like the whole of the statistics. The reason why I'm leaving this here is because is each trial statistically similar? If so, should the data be merged? Is each concentration different from other concentration? Our statistics our descriptive and distribution statistics are going to tell us that information. So the reason why I'm leaving this card here is it's more here. I want to determine if each trial is statistically similar and if it should be merged so that there are less rows of data. This basically so that the possibility of reducing computational resources has been addressed. I'm gonna get rid of this part here. Our acceptance criteria is going to be, is each concentration different from other concentrations should the data be merged? So this is our treatment plan. We're basically trying to figure out what data we could potentially drop. And that's going to go statistics. I want to do this at the same time. Then execute statistics. This is a statistician card. This is absolutely what we're going to be focusing on this upcoming week. So here under data science, I have a sprint. Under statistician, I do not. So I'm going to do a sprint 0306. And my card timer here. And this is probably going to take, gonna put 10 hours. Running the stats takes a while. Because you have to set up your cards. And it's just a lot. Our card size here was 8. Yeah. So this is from our domain expert. So we know we have something from our statistician. Our treatment plan for present data. I feel like this is gonna happen after here. And I want this to go here. After the report. Okay. This might not happen this week. This in statistician, it might not. It might be next week. But it's still going to be on this particular sprint. Here, I think I want to get up to transformations, and then we'll move forward with modeling. I think that's a good transition point for the project, because these transformations and split into target and feature and train test validation splits, that's like you're moving into modeling at that point. Find external data sources. I don't have that listed yet. Let's go ahead and share. I'm gonna put 4 hours on this, just because we have to look up some formulas and determine if it's viable or not to pull in. And it has 8 story points. Developing new features, you can spend ages doing this, but it's not particularly difficult. Just takes time. So instead of 8, I'm actually gonna do 4. Statistically different. Okay, and we're confirming that in these later stages when we're getting to the reporting. This new features, okay. I want to copy this card. This, I don't want to spend more than 2 hours on this, because, you know, creativity is great, but, you know, ideas can get more and more outlandish as time goes on, and I don't want that. Run descriptive stats. This card size I'm going to make be 8, and the reason why is because we're pulling in multiple libraries. You know, running the base Python versus the NumPy or SciPy. Sometimes information gets stored in the decimal points of our data, and libraries do that differently or handle that differently. And so I want to make sure that the values that I'm getting for descriptive stats are the true and actual values. One way to do that is to just run them all and then compare them, and then, you know, read up in the actual documentation which one is doing what. I don't know what happened. I pressed a key on my keyboard, and it's not tied to anything. Nope. Okay, never mind. Let's go here. Right now we are talking about running descriptive stats. That I'm gonna put 4 hours down just because it can be a lot. The developing visualizations. Okay. In theory, this should not take that much time. However, it's complicated for me, and I know that it's complicated for me. I am not the person that you want to do this. I can look at a table and get the same value out. But, you know, visualizations are really important. But you want to make sure that you assign this to someone on your team that is a visual learner, I guess you could say. I'm not. I'm a kinetic learner. I need to interact with something. So me running these statistics and going through is what's telling me the information. It's not the actual visual. So I'm putting 8 for me, but in all honesty, it should be like a 2. Your visualization should be super easy to develop. And again, because it's me, I am putting a total of, for like all visualizations on this project, I might spend a total of 8 hours. I'm going to put 1 hour here because I want to dedicate at least that amount of time to trying very hard. And I might skip it and come back. Not going to lie. Then run distribution stats. Again, I'm going to do 8 because you're comparing libraries and doing a lot of code. It's repetitive code, but it is a lot of code. And you're having to import libraries and make sure that those are in your environment. I'm going to put 4 hours here. In all honesty, it should not take that long. Both of these tasks should take 4 hours together. And it's not 2 hours each. It's kind of like the descriptive stats might take 30 minutes, but the distribution stats might take the other 3.5. So these two things I usually do together. You know what? Let's go ahead and change it to update it to that. Let's do 1 hour here. And then they have the same amount of story points, but they take different amounts of coding. 3 hours there. Like this descriptive stats is like 1 or 2 lines of code. Or you can do it in 1 or 2 lines of code. The distribution stats, it is like 30 to 40 lines of code. And then we want to develop our visualizations. Here, I think I put 8 on the other one. Yeah, I'm gonna change that to 4. Because again, I don't want to spend terribly long on it. Card size, I'm going to put as 4. I don't know if I copied this or not, so I'm going to go ahead and copy that. And we're starting to get to the point where, and I'm going to spend at least a solid hour on that. This is starting to be a lot in one sprint, but if we're planning for 2 weeks, then we're doing pretty well on that. It is a lot. This treatment plan I want to kind of leave alone, and then I might do like these 4 the following week, because this is a lot of work. Like this create a pipeline, this is going to be like our first kind of like big card. This is like a 32. So it's 2, 4, 8, then 16. Yeah, then 32. This is a big job. And the report section, this is again, we're introducing an entirely different aspect of the code for the first time. This is another big thing. And then execute statistics to summarize present data status. So I think I'm going to leave these for the following week, because these are kind of like big things that take resources. So pipeline for all statistics. And then here I'm going to put create a pipeline for data transformations and splits. That's going to be what comes next here. And we're going to do that before we move into modeling. So basically pre-processing, again, you can make a pipeline once you have a client that you know that you're going to get repetitive data from, once your file types and everything have been established. And of course, if they ever update how they're storing their data, you have to update too. So I don't necessarily want to pipeline those particular things, but once I move to pre-processed data, that's after the scrubbing is done and we have exported and we can import. Similarly, once we have that done, like all of this needs to be pipelined. This external data sources, like you need to, if you're pulling that information down from the website, you need to do that. If you're calling on a database, you need to do that, and that needs to be pipelined because that needs to be read into every project, right? And then these new features, like that needs to be pipelined too. So I think I might add that here for gathering external data and creating new features. These are the this is something that should happen here. Like that's the time it's going to happen, but I think I'm going to do this pipeline at the same time as I do the statistics pipeline. Yeah. Because otherwise this would be all that I do that week, and I really want to get into some statistics. I'm itching for it. And that's the thing is, you know, project things don't necessarily have to be done in order. That's something to remember too. Okay, that is all that I'm going to stream for this particular project management section today. If you have any questions, feel free to pop into the comments. I just realized the music level is really, really low, so I can hear it, but y'all might not be able to, and I apologize. If you have any questions, feel free to pop into the comments and ask anything. Yeah, I will see y'all next Monday for the same thing. All right, bye.